Hello, y'all. Welcome to lesson 62 of my DP chemistry curriculum. Today we're doing structure 3.1.6. We're going to talk about oxidation states as a number assigned to an atom to show the number of electrons transferred in forming a bond. It is a charge that an atom would have if the compound were composed of ions. So this is a little weird and a little bit hypothetical that we're going to be going through, but we'll do a bunch of examples to help you out. We're going to be able to deduce the oxidation states of an atom or ion or a compound, explain why oxidation state of an element is zero, and a couple things to note about all this. Oxidations are shown with a plus or minus followed by the number, like +2 or -1. However, when we often talk about charges, we usually do 1 minus or 2 minus or 3 minus, so it's a little backwards from charge. The term oxidation number and oxidation state are the same. You can use either one always and forever. Just make sure do not be confused from that. Lastly, we're going to talk about naming conventions for oxyanions, and we're going to use oxidation numbers with Roman numerals. We've kind of done this already way in the beginning when we were talking about ionic compound nomenclature. So we're actually not going to review this section. But further inclusions of polyatomic ions that we will continue to name as normal are nitrate, nitrite, sulfate, and sulfite. So you still need to know those polyatomics because regardless of oxidation state, we're going to use their proper names. So with all that preamble out of the way, let's talk about oxidation states. And I'm going to spend the rest of this abbreviating as O.S because I do not want to rewrite the word oxidation states 100 times. So when we do any sort of compound formation, ionic compounds are quite easy to know the charges. So in an ionic compound, such as NaCl, we know the Na has a charge of plus and the Cl has a charge of minus. If we're using numbers, we'll do 1 plus and 1 minus, but we don't when we have 1. So maybe another example might be MgO. This will be 2 plus and this will be 2 minus. So we know the charges of those compounds, and that's because electrons are transferred. So it's pretty easy with, I don't know where that one came from, transferred. It's pretty easy with ionic compounds to know the charges of the atoms. But the problem is in a covalent compound, so let's take, for example, water, H2O, these don't have charges. So how do we figure out the charge of the individual atom? Or how do we figure out electron transference? Or specifically, how do we assign loss or gain of electrons? So that's the big question. Where are these electrons going? And that's where we create oxidation states or oxidation number. This is specifically a number assigned to an element, and that's going to show the number of electrons lost or gained through bonding. It doesn't always have to be bonding, but just in general, we look at it through bonding. So we're going to figure out how many electrons maybe the oxygen or hydrogen generally lose or gain. And of course, if we're talking about the loss or gain of electrons in a bond, this is purely going to be based on electronegativity values. Furthermore, this is a hypothetical loss or gain because in covalent compounds, electrons are shared. And so there is no full loss or full gain. It would be more applicable to use like um, decimal values to say we gained about half an electron's worth, or percentages. The electron is there 40% of the time. But in oxidation state, we're using whole integer values. So we're going to use whole numbers to dictate a loss or a gain. So there's a couple things that we do know. The first one that we must keep in mind is that oxidation state does not equal charge. So if something has an oxidation state, that does not necessarily mean a charge. If we look at sodium, for example, the oxidation state, or a sodium ion, the oxidation state would be 1 plus, or sorry, +1, and the charge is 1 plus. Even though these values are numerically the same, they are not equivalent in terms of chemistry. An atom having an oxidation state does not mean it has an ionic charge. We also have a lot of rules. So unfortunately, oxidation state has a lot of rules that you have to remember and you have to be able to use confidently. When you go through these rules, it will get easier over time and you'll start internalizing them, but you need to practice a lot to get it straight. So rule 1, and these rules also are in kind of a hierarchy. Start with rule 1 and work your way down the list, and that's how you're going to figure out oxidation states. The first rule is pure elements have an oxidation state equal to 0. And that's because our distribution of electrons will be the same between elements. And this kind of makes sense because we said we're basing this on electronegativity values. So if we look at hydrogen bonded to hydrogen, the electrons are going to be right in the middle. They're not going to be to the left or to the right. They're going to be smack dab in the middle, which means they're going to be shared evenly, and therefore neither of them will develop a charge. So H2, each hydrogen has an oxidation state of 0. Because they're not moving, the electronegativity values are the same. So if we look at a bunch of examples, if we look at the oxidation state of sodium atom, that's going to be 0. If we look at the oxidation state of Cl2, chlorine, that's going to be 0. If we look at the oxidation state of phosphorus 4, that's going to be 0. So no matter what, an element or a pure element or a pure substance of just one element will always have an oxidation state of 0. Number 2, monoatomic ions, so ions that are one atom, atomic ions, have an oxidation state equal in magnitude to ionic charge. So, for example, because remember, charge and oxidation state are not the same, the magnitude still will be. Copper 2 plus has an oxidation state of +2. Oxygen 2 minus has an oxidation state of -2. Fluoride minus has an oxidation state of -1. We do not get rid of the 1 when we're talking about oxidation states. -1 is -1. We do not just call it minus. All right. The first two rules are pretty simple. We're just kind of assigning charge to the charge bit. You'll even notice that sodium is also 0 because the charge is 0. Chloride, the charge is 0. Phosphide, the charge is 0. Or chlorine and phosphorus charges are still 0. All right, number 3, oxidation states of atoms in a neutral compound sum to 0. So, for example, Na2O. In this ionic compound, sodium has a charge of plus, oxygen has a charge of 2 minus. Therefore, their ion oxidation states would be +1 and -2. We have 2 sodiums. So if we just pull where these come from, this whole thing is going to sum to 0, the overall charge of the compound. So the charge of the compound is equivalent to the sum of the oxidation states, and that sum will always be 0 in a neutral compound. So then what if your compound is not neutral? Well, that happens when we have polyatomic ions. So oxidation state of a polyatomic ion must sum equal to the charge of the ion. So for example, one of the most common polyatomic ions is hydroxide, OH minus. Once again, oxygen is -2, hydrogen is +1. Together they equal -1, which does in fact equal our charge. If we look at any of our other compounds, like, oh gosh, now I have to think of an example. Ammonia, ammonium, NH4 plus. Nitrogen is -3, hydrogen is +1, but we have 4 of them. That will be +1, which does equal our positive charge. So when we have polyatomic ions, that sum will equal the charge of the ion. So that is rule 4. We have 2 more to go, and unfortunately these will be the hardest 2. Rule 5. Oxidation states of atoms are typically, not always, typically the charge of the most common ion. So what the heck do I mean by that? Well, for example, group 1 elements, or specifically group 1 metals, because I want to take out hydrogen. Group 1 metals are almost always +1. Group 2 metals are almost always +2, and that is their most common ion. Group 17 elements are almost always going to be -1. There are some exceptions here. So this is unless bonded to a more electronegative element, such as fluorine. So if fluorine and chlorine are bonded to each other, fluorine will have the minus charge, chlorine will become positive. And then we have 2 more here. Oxygen is almost always going to be -2. There is some rare examples, and that's unless peroxide. Peroxide has a charge of -1. So if you ever have peroxide or hydrogen peroxide, the oxygen will be a -1 oxidation state. And then lastly here, hydrogen is almost always +1, and this is unless a metal hydride, like NaH, then that would be -1. So sodium hydride will be -1 on the hydrogen because the metal will overtake hydrogen's need to become positive. All right, so that's rule 5. And finally, our last rule, rule 6. We assign positive oxidation states. I'll write positive out. Maybe I'll try to write it out. Positive oxidation states to the most metallic element first. So that means furthest left and bottom of the periodic table. Then we assign our negative oxidation states to the most non-metallic element first. So furthest up and to the right towards fluorine. Then we just figure out the rest from math. The rest is found through algebra. So this is my little abbreviation. This is my little separation from what the book teaches. They don't really mention algebra. They just figure you know how to use it, but I find it a good reminder. So let's look at an example. If we look at the compound potassium permanganate, KMNO 4. How do we figure out the oxidation state of the potassium, the manganese, and the oxygen? So the first thing we have to look at is the compound is neutral. There is no charge, which means the sum of oxidation states according to rule 3 is going to be equal to 0. We're going to assign the positive oxidation state to the most metallic element. So between potassium and manganese, potassium is more metallic. We know that potassium is group 1, so it's going to have an oxidation state of +1. Then we assign the negative oxidation state to the most non-metallic element. Well, that's the only one here is oxygen. Oxygen will have an oxidation state of -2, and we have 4 of them. So we're going to multiply by 4. Then manganese. We don't have a rule for manganese. So we're actually going to just represent manganese as X. And we're going to sum these up. So when I sum them up, I get +1 plus X minus 8 equals 0. X is equal to 7 plus 7. So this is just algebra. I combined 1 and -8 to make -7, brought it to the other side to make it +7. So our oxidation state for potassium is +1, for manganese is +7, and for oxygen it's -2. And this is how we figure out oxidation states. So basically what we're saying is that within this compound, if we are to arbitrarily or hypothetically assign electrons, potassium has lost 1, manganese has lost 7, and our oxygens overall have gained 2 electrons each. And so this is what oxidation state is used for, to figure out the relative charge or loss or gain of electrons. This seems like nothing really big now, but when we move into redox and the movement of electrons in chemical reactions, it will become incredibly important to be able to track oxidation states. So what we're going to do is 2 more examples. We'll do like 4 more examples, and I'll write them out, and you can pause the video and then try them at home. But you want to find the oxidation state of each element in these 4 examples. And these last couple are going to be a little difficult. You know what? That is actually part of the other one. All right, so pause the video, try and find the oxidation state of nitrogen, oxygen, aluminum, sulfur, and oxygen in all of these. Otherwise, come to the video now, and I'm going to go over it starting now. All right, so this is only nonmetals. Oxygen is more nonmetallic, and according to rule 5 and 6, it's going to be -2. The overall charge is 0, so then therefore nitrogen, which is X, must be +2. So nitrogen has an oxidation state of +2, oxygen has an oxidation state of -2. In nitrogen dioxide, oxygen is still -2, but we have 2 of them. Again, the overall charge is still 0. Therefore, this time our nitrogen must be equal to +4. So nitrogen is +4 oxidation state, oxygen is -2. All right, moving on to aluminum sulfate. And I actually made a mistake here. Hopefully you figured that one out. Otherwise, you're just going to have double my answer. So in aluminum sulfate, the first thing I know is that sulfate, SO4, has a charge of 2-. So what I'm actually going to do is break this into 2 parts. I'm going to do aluminum 2 and big X 2-, 3. And then I'm going to do a separate one where I'm just going to do sulfate 2-. So for my first one, this whole compound right here that's going to be 2-, and we have 3 of them. Sorry, -2, and we have 3 of them. And aluminum will be X, and we have 2 of them. And that's going to equal 0. So this is going to be -6. This is going to be 2x. That's going to be equal to 0. So 2x equals +6. X equals 3. So aluminum is equal to 3 plus positive 3. Sulfate, on the other hand, the whole thing is equal to minus 2. And I know that from that minus 2 minus charge. Oxygen is each negative 2, and we have 4 of them. Sulfur, on the other hand, will be our X. And so therefore, X is equal to X minus 8 is equal to negative 2. X is equal to positive 6. Sulfur is equal to plus 6. Oxygen is equal to minus 2. And aluminum is equal to plus 3. And there are all our oxidation states. So I hope this helps you understand how to calculate these and find these values, as you will be using them a lot later on. And so have a great day.